discuss an important topic of solid state chapter, that is packing efficiency. And this topic is important to understand how the particles arranged in space. And this topic is also important for various competitive exams. So let's start. So the first question arises, what is the packing efficiency? So the basic definition of packing efficiency is the percentage of total space filled by the particles. That is packing efficiency. So to understand the packing efficiency, let's get an example. So let's assume we have a number of balls and we have a box, and we have to fill these balls inside a box. So we can fill these balls in a various ways. So I will fill these balls like one by one to cover the maximum space of the box. After filling, still we can see there are some vacant space, and this space is called as void, and the volume which is covered by these balls is called as packing fraction or packing efficiency. So now the question is, what is the difference between packing fraction and packing efficiency? So the basic difference between the packing fraction and packing efficiency is the packing fraction is calculated with respect to 10 and packing efficiency is calculated with respect to 100. Let's understand through the formula. So the formula of packing fraction is Z into small e by capital E. Here Z represents number of particles present in space, and small v represent volume of particle. Volume of particle, and the capital V represent volume of space or unit cell we have. And the formula of packing efficiency is similar to packing fraction, but the only difference is it is multiplied by 100, because I have already told it is with respect to 100. So let's understand the packing efficiency formula through an J2010 problem. So the question is, we have given a diagram like this, a square, and each corner has one circle like this, and one circle drawn in between the square, and we have to calculate its packing efficiency. So how we will calculate? So this is a square, so each side will be equal in length. So let's assume this is side length A. So this will be also A. It is a two-dimensional diagram. So the packing efficiency formula, in place of volume we will use term area here. So the formula will become packing efficiency is equals to Z into A by A dash. Here Z represents number of circles and this A represents area of circle, and this A dash represents area of the square. Area of square. So let's calculate the Z. Z is the number of circles present inside the square. So here we have 4 circles which are present in corner, and each circle contributes only 1/4 part of it. the circle present inside the square contribute the whole part. So we did consider 1. It contribute the whole part and this contribute 1 by 4. So the number of circles is 1 by 4 into 4 plus 1. Why 4? Because there are 4 corners, so there are 4 circles. So the value of Z will become 2. And then substitute these values in packing efficiency, which is 2 into area of circles. We all know pi r square, and area of square is a square. Why a is the edge length. To simplify this, we need a relation between a and r. So let's derive relation between a and r. So consider this diagram and draw a diagonal. And the circle this. Now name it A, B, C and this. From the triangle ABC, angle B is 90 degree. So we can use the Pythagoras theorem to calculate the length of AC. What is Pythagoras theorem? Hypotenuse square is equals to base square plus perpendicular square. So we have already tell that this length is A. So we can put here A square plus A square equals to 2A square, which is AC is equals to under root 2A. And from the diagram itself, we can see AC is, this is part of circle. So from the center to its circle, distance is R, and this is the diameter of this circle. So this distance is R, and this is also a radius of the circle. So total R plus R plus R plus R is 4R. From the equation 1 and from the equation 2, we can equate this equation because their LHS are equal. So RHS will be also equal. So root 2A equals to 4R and A is equals to 2 root 2R. Now we will substitute this A value in the here we have already discussed this formula. So packing efficiency is equals to 2 into pi r square divided by, in place of A, I will write 2 root 2 r, which is square. After solving this, we will get the value of 78.5%. It means 78.5% of the square is filled by the circle and remaining empty space will be 100 minus 78.5%, which is 21.5%. Similarly, if we have this diagram in 3D space that I have solved later. So firstly let's draw the diagram. It is a FCC unit cell. It is similar to previous question, but the only difference is this is a 3D diagram and that one is 2D diagram. So to calculate its packing efficiency, the formula we will use here is Z into V. Here we will not use the term area. Here we will use volume of sphere. and this is the capital V is the volume of the cube. So before calculating the volume of unit cell, this is the length, this is the breadth, and this is the height of the cube. And this is the cube, so all the sides of the cube are equal. So A is equals to B is equals to C. Before calculating the packing efficiency, we have to know that each corner atom of FCC unit cell contribute only 1/8 part of it, and each face atom contribute 1/2 part of it. So firstly calculate the Z. Z means number of atoms contributed here, which is 1/8 into 8 plus 1/2 into 6 is equals to 4. Why 8? Because there are 8 corners, and why 6? Because there are 6 faces and each faces constitute one atom, which contribute only half part. Now substitute these values in the formula. The packing efficiency is equals to 4 into volume of sphere, which is 4/3 pi r cube, and why we are using sphere volume? Because we consider atom is in spherical in shape, so that's why we are using here the volume of sphere, and the volume of cube is a cube. Here a is the edge length of the cube. To know the relation between A and R, from the previous we get the relation between A is equals to 2 root 2 R. This diagram is similar to that previous one, so I will not repeat it again. We will directly use this formula. The packing efficiency is equals to 4 into 4/3 pi r cube equals to 2 root 2 r cube. After solving this, we will get the value 74% by substituting pi as 3.14. The percentage of empty space is 100 minus 74%, which is 26%. Similarly, we can calculate this for SCC, BCC and SCP. So for SCC, the packing efficiency is 52.4%, and the percentage of empty space, also called as void, which is 47.6%. And for BCC, it is 68%, and here it is 32%. And for FCC or HCP, because both have similar arrangement, so both have packing efficiency 74%, and here it is 26%. Conclusion is, on comparing all these three, FCC has highest packing efficiency and lowest empty space. So FCC has best arrangement of atoms among all these three. So thank you. This is from my side.